Alright, so in the first video from chapter 30, I'm going to talk about magnetic fields and forces, and this covers chapter 30-1 and 30-2 in the textbook. Alright, so a magnet, I'm sure you played with magnets at some point, can exert a force at a distance on certain metals or on other magnets. So this is actually another type of fundamental force, like we had gravity and the electric force was another fundamental force, or other fundamental forces. And it's an action at a distance, so you can think of it as a field force, just like the electrostatic force was. So as it turns out, magnetism has actually been known a lot longer than electricity has. It's known since ancient times. So the Greeks actually knew about lodestones. So lodestones are just natural magnets that you can dig up out of the ground. And the Chinese, in fact, have been making compasses since like the 12th century. So magnets have been known for a long time, although really the reason how magnetism works wasn't understood until much more recently. Okay, so as it turns out, and we're going to talk more about this later in this chapter, so the source of the magnetic force is actually moving charges. So people didn't actually figure this out until the 19th century. And it's convenient to use the magnetic field similar to what we had for the electric field. So remember, the electric field was a way to picture the electric properties of some charges. So we're going to use magnetic field to picture the magnetic properties of certain objects. And we're going to use a letter B to stand for magnetic field. So you can think of this, a good way to show magnetic field lines are to use iron filings. So these little bits of iron. So you drop them around your magnet and it'll actually, filings tend to line up with the field lines. And the way you define these things is the direction of these field lines is given by a compass. So the field lines always point in the north direction. So you take your compass, you put it by a magnet of some sort, and whichever way is pointing north, that gives the direction of your field line. So this is kind of what it looks like. So here on the left-hand side, we've got a bar magnet. And if you drop the iron filings, you'll see the iron filings tend to actually line up along the field lines. And that actually is what's shown on the right, is what these field lines look like. And again, notice that the field lines are always pointing from north to south. Okay, so speaking of which, so we define two types of magnetic poles. And again, for historical reasons, we call them north poles and south poles. And similar to what we had with charges, so like poles repel, so a north and a north or a south and a south will repel each other, but the opposite poles attract, so north and south attracts. So a bar magnet is a magnetic dipole because it has two poles, a north and a south, and they're separated by some distance. Now another interesting thing actually, if you take a bar magnet, which has a north pole and a south pole, and you break it in half, what you actually get are two dipoles. So, and each of those has a north and a south, and a north and a south. And as far as we know, nobody has ever observed what's called a magnetic monopole. So a north all by itself or a south pole all by itself. Magnetic poles always come in pairs as far as we know. And again, people actually look for these things. There's nothing that expressly forbids them, but as far as we know, in magnetic poles, they always come in pairs, so a north together with a south. Now, in a consequence of this, so if you remember in electricity, well, we had our electric field lines always ended on positive or they started on positive and ended on negative charges. But in magnetism, since there aren't the source, we don't have this source of the magnetic field like a magnetic monopole would be, so magnetic field lines, as they turn out, never end. So they always end up being closed loops.